These are the two leaves of a plant. Now, if you see them, these are the two leaves which are running parallelly to each other. Now, if I name one of them, for example, this as mathematics and this as physics, as both of them are running parallelly to each other, the question is that do they meet at some place? This mathematics and this physics, these two parts running parallelly to each other, do they meet at some point? Although they carry the same root out here, running parallelly, do they meet at some point? Well, to be very honest with you, yes, they do. Parallel projections and parallel lines diverging meet at some point, and we are going to talk today about that, where the parallel lines meet, and that is called non-Euclidean geometry. In other words, what we called differential geometry. A very good morning and a warm welcome from Physics for Students. My name is Shaunak, and today we are going to discuss about a very important and demanding topic.
Well, when we talk about these two terms, differential and geometry, obviously these are the two words that comes to our mind. So what we need to know from here is that, for example, what is differential? We are okay with the term geometry, but what is differential? So by our common sense and our high school mathematics, what we know differential is something which will be related to, or we will do differentiation. Right. But when we talk of differentiation, the obvious thought that comes into mind is our calculus. So we are okay with the right hand term or the word geometry because we know what geometry is all about. But about differential, it should be something related to differentiation, and differentiation can only be done through calculus. So from that we can finally deduce that the definition would be a study of geometric properties using differential and integral calculus. Yeah, mostly differential, because in differential geometry we mostly use differentiation, but yes, we do integral part also, but in case of calculating the volumes of surfaces, but here we do mostly differentiation.
Now, having laid down the foundation of differential geometry, I would like to tell you that because it is a basic introduction to differential geometry, you note that in this picture I have laid down that there are two branches of differential geometry. First one is a pure research branch, okay, where people go into pure mathematics and pure research, and they go deep into studying differential geometry, various notions. And another part is called how much it is related to general theory of relativity, right? So what we are going to do is that we are going to look more into the differential geometry which relates to general theory of relativity rather than into pure differential geometry, which that is much more related to research. Now, if you can look into this picture, I have laid down that there are two branches. The pure differential part is one is Riemannian geometry, which is also called elliptic geometry, invented by Bernhard Riemann, one of the Euclidean geometry that completely rejects the Euclid's fifth postulate and modifies the second postulate. The pseudo-Riemannian geometry generalizes Riemannian geometry to the case in which metric tensor is positive definite. The Finsler geometry, named after Paul Finsler, takes care of the geometry which deals with Finsler manifold. And just to tell you, Finsler manifold is just is just the Riemannian geometry without the quadratic restriction. Symplectic geometry is a branch of differential geometry, again with studies with even dimensional manifold whose structure is determined by distinguishing closed non-degenerate two form. And conformal geometry, as the name itself suggests, conformal means angle preserving. It is a study of the set of angle preserving transformation in a space. So now, and on the right hand side, you can see that when we speak of general theory of relativity, it deals with tensor, metric tensor, affine connections, Christoffel symbols, Riemannian curvature tensor, Bianchi identity, all those things. So that is basically the goal of our study, that we are dealing more into the general theory of relativity part, not into the pure differential geometry. But yes, before we start, I thought that it is better to give you a thorough idea of what are the two branches of differential geometry and what comprises of what. So from this part, which you can see in the picture, I have laid down what is differential geometry. Now, if you can see that it also shows that it also, studies smooth manifolds. Now, before I go ahead and start with today's topic, I would just like to tell you that the basic idea of today's video is that we are going to understand on a basic notion what is differential geometry. One. Second, we are not going to look more into the mathematical part of differential geometry because this video is just an introduction to differential geometry. So it would give you a basic idea on what is differential geometry, how you can start reading differential geometry, what are some of the common confusions which arises, some common questions, and a little bit about the background. And I would request you watch the video till the end because you will find a lot of interesting topics. Now, while we read with the earlier definition of differential geometry, you must have seen that we read something which is called a smooth manifold. Right. It also deals with smooth manifolds using linear algebra, multivariable calculus, all those things. So here is a basic idea, very basic. I'm not going again into the mathematical part. Very basic idea on what is a smooth manifold. You can read it out, which is there on your screen. So you can see that it looks something like Rn or the n dimensional the Euclidean space, but globally have got some topological structures. That means it deals something which has got we can apply calculus on the part of the local manifolds, but globally, if I see it on a global level, it has got nice topological structures. So I think that till now things are clear why differential geometry, why it is called differential, and the concept of smooth manifold. Now, just to give you an idea, because definitions are not always sufficient, here are some of the examples of smooth manifolds just on your screen. So other than Euclidean spaces, there are circle, which is there, parabola, sphere, torus, paraboloids, ellipsoids, hyperboloids, and there can be anything which are other dimensions. So just to tell you, if you can have a note out there, so it is something which is local, something local like vector space where we can apply calculus, and globally it has got a differential structure. Now, because we have to, apply calculus, so you can understand in general in differential geometry, volumes are used by, calculated by using integration part of the mathematics, and manifolds are differentiated using differential calculus. So how this name suggests differential geometry. Now, also another important thing is that because the manifolds require some means of mathematical integration and differentiation, hence the first requirement of transferring the ideas of calculus to manifolds requires this smoothness. So for the simple examples, now one thing you see that for the simple examples which I have given, torus, sphere, etc., these are some of the, we can say that these are some of the subspaces of the main Euclidean space. These are some of the subspaces of the main Euclidean place. Now, for example, on an intuitive level, it is very easy to describe what it is. Now, have a look into this picture, right? So, this picture actually shows that if you want to call a curve smooth, what does it mean? It means that it has a tangent line that varies continuously from point to point, which is the curve. If you want to call a smooth surface, then it should be one that has a tangent plane that varies continuously. Now, here is the catch. The catch is that in case of a smooth curve or a smooth tangent plane, you can say, okay, the tangent line is varying continuously, the tangent space, a smooth surface is one where the tangent plane is varying continuously. But what about something abstract? For example, when we deal with general theory of relativity, we have something which is called a Lorentz metric, where we are dealing with n-dimensional or four-dimensional space-time. Now, what happens is that the four-dimensional smooth manifold that carries a general geometric structure, generally which is called a Lorentz metric, here we cannot define a particular object. For example, a curve or a space which varies smoothly, etc. So what happens is that we need to think smooth manifolds as topological spaces or abstract spaces. Now, the most important thing that you need to understand that why we are going abstract, that is most important before we go further into differential geometry. Now, if you see, for example, torus, for example, figures in general Euclidean spaces, these might be called as these are sub-objects of a particular space, which is a Euclidean space, A, B, C, whatever. But when we move into the very abstract areas where general theory relativity, n dimension, 4 dimension, where we cannot mention those smooth manifolds in terms of specific objects, we require abstractness. That is where abstractness comes, and that is where the difficulty also arises, because in general for human being or for the starters it is difficult to visualize abstract spaces, right? How do we visualize an abstract space? So but abstract spaces give us this benefit that we will see it soon, that how it can be generalized in an arbitrary coordinate structure. So the need of abstractness arises because we go further into complex mathematics and science. Things cannot be defined with some concrete, describable concrete objects. So that is the need, that we need abstract objects. Now this is a very common question which comes in the mind of the starters, or even to me when I started reading differential geometry. Which one should I study first? Geometry, differential geometry, or topology? Now, this is a question which I have talked to my seniors, professors, etc. And I want to give you a kind of an, my solution is that start with differential geometry first and then go with topology. The reason is that you need to understand, see, as you see in the screen, I have tried to explain that differential geometry you will get in topology, topology you will get in differential geometry. So, the idea is that both of them are overlapping with each other, but there is a catch. The catch is that in differential geometry is easy. Why? Because differential geometry deals with local areas. I mean to say abstraction is at the local level, whereas topology deals with much higher abstraction, which is on the global level. So just to give you a small tip, start with differential geometry first. The reason is that topology does not depend on differential geometry, because topology deals with much larger things than mere abstractions, mere differentiation of manifold. It deals on a very higher scale. So in order to go to a more complex and larger calculations and understanding, start with the local one. Think of something, you start first swimming in a small lake at your place, then you pond, then you go to the lake, and then finally you try out jumping into the ocean. So before you start jumping into the ocean, start dealing with the differential geometry part, which deals with abstraction and complex concepts at a local level. And then you can go into the topological part. However, you can do whatever you want. You can start with topology and go into differential geometry. But from my side, I would say differential geometry is easier. At the beginning of the video that we use calculus, look at those figures. These figures always have angles. The triangle, whatever the figures that you are looking, right? These all have corners, and that is what we technically call angles or corners. Now look into this picture. Can you see any angle? Can you see any corner? No. So it is simple, because when we are dealing with corners, we cannot, we have to use differential calculus, because we can use derivatives and we can keep on calculating the derivatives as long as we want. So the answer is very simple, because we do not have corners, because we do not have angles, so we need to do calculus in case of smooth structures. So you recall what is smooth manifold? So these figures, they don't have corners, and we need to differentiate as long as we want, and that is why we apply calculus to differential geometry. Before cracking our head into the details of any subject, this is an interesting topic. Why should I learn differential geometry, right? We are learning calculus and all those complex calculations, investing our time and cracking our head throughout day and night. So why should we learn differential geometry? Now, first of all, we will come more into the details, but the basic motivation of differential geometry is that it is absolutely coordinate free. Now, when we talk that it is absolutely coordinate free, what do we mean by that? That, for example, that formulating physical theories in terms of abstract coordinate and free manifolds is that it, for example, at that particular coordinate system, somebody is performing some kind of an experiment. This particular coordinate system, somebody is performing some particular physical experimentation. Both of them, both the things will match. Because two scientists in different coordinate systems develop the same theory, but because it is coordinate free, that means that person and this person are not dependent on each other. So both of their theories will match at some point of time. So they produce the same results, mind it. So that, and you see now how it is related to general theory of relativity, because as I have speaking in my lectures, the general theory of relativity is a system of abstract coordinate-free structures of space-time. So obviously, if you're taking something which is coordinate-free, a person performing experiment here should match with here. So how do we do that? That is the beauty, and we should learn differential geometry. It gives you the advantage of making coordinate-free calculations. For example, general relativity deals with something called global positioning satellite, GPS. So it is one of the reasons that we should learn differential geometry. I mean to say the practical application. Here is a small clipping which will give you a further motivation and understanding why you should learn differential geometry.
Well, in electromagnetism, we have an elegant formulation of terms in differential forms. So the generalized Stokes theorem for differential manifold is important. So there is an usage of differential geometry in electromagnetism. When we talk of robotics, geometric control theory is used as differential geometry a lot to study the control of nonlinear systems. In general, we draw approximation of nonlinear system with linear system, but as the machines become more complicated, we use differential geometry. For quantum field theory on a higher dimension of manifold, differential geometry becomes extremely important. Economics uses a term called econometrics. It is basically an application of statistical methods to economic data to give a quantitative analysis of the economic phenomena. So we use differential geometry, which is called econometrics in economics. In chemistry and biophysics, modeling of cell membrane and their varying pressure, etc., are measured through differential geometry. Engineering, it is used to solve problems in digital signal processing as well as in image processing using differential geometry. We use probability theory so that we can interpret various structures using Riemannian manifold, which are much more complex. And we also use structural geology to describe different complex geological structures. And to mention more, the famous mathematician Grigori Perelman used the beauty of differential geometry, which is called the Ricci flow, earlier discovered by Richard Hamilton, to solve the famous millennium problem called the Poincare conjecture. So all these different usage, and there are more, which lays out the usage and the importance of differential geometry in terms of practical applications.
Now, one thing also what I would like to tell you, right on your screen I have given kind of a link. I have also given that link in the description, that application of differential geometry to molecular genetic. How beautiful it is. Now let me read you a small abstract of these three gentlemen's paper, which is quite a long back. It is something very recent. So it says that a mathematical formulation is proposed in which changes in information content of an evolving DNA molecule may be described. The basic construction is a 65-dimensional differentiable manifold in a coordinate structure such that the manifold points represent the number of each codon. Now, codon means it is a sequence of 3 nucleotides which form a unique genetic code in a DNA. So it is a 65-dimensional differential manifold in a coordinates such that the manifolds points represent the number of each codon type in a DNA molecule. It is shown that this manifold cannot be Euclidean, at least conditionally to be Riemannian. See the beauty of differential geometry. Apart from electromagnetism, biophysics, which you have already seen, differential geometry can also be applied to genetics. Why? Because it is a 65-dimensional thing, and obviously it is a Riemannian geometry. So the application goes up to this level. A very pertinent question. Well, you might be smiling, but yes, this is the question. Is differential geometry difficult? Now, if I talk in a general sense, I would say no. Because differential geometry intrinsically is not difficult. Only the problem with differential geometry is that it combines, I have taken a note, mathematical analysis, geometry, topology, and algebra. So what happens is that when you are learning differential geometry, it is assumed that you know multivariable calculus, linear algebra, metric tensor, vector analysis, quadratic equations, integration, calculus on manifolds, lot of things. So to be very honest with you, I would say no, differential geometry is not difficult, but yes, people find it difficult because they have to know a lot of other things in order to learn differential geometry first. So my advice would be that just hold on, I am coming up with a new video on how to learn differential geometry, just the way I did how to learn, how to learn general theory of relativity. I am I'm on the process how to learn differential geometry so that you can come up step by step and you can understand what are the steps required in order to learn differential geometry, what are the books that are required, and how you would go ahead. But for the time being, no, it is not difficult. Only you need certain preparations. There is a process, there is a guideline, there is a method how you would go. Yes, it requires time, but it is not difficult. So if you go and proceed step by step, you can learn differential geometry. Any deeper understanding of a particular subject demands that you should go back to the past. You should learn how these concepts came into being. You should learn what our ancestors did, what are the problems they faced, and today, whatever we are reading, we are learning, we are enjoying the science. These are being developed with a certain pace of time, with a certain sequence. So, this part of our video will concentrate on what is called a history, or rather the process of development of differential geometry. I know it is quite a long subject, it cannot be told just in a small video like this, but here is my humble attempt just to lay you down that what are the basic ideas and how differential geometry developed. Note to the viewers that there are much more than we can discuss, which is outside the scope of this video. Here is a small kind of a presentation on the developments of differential geometry.
Well, to give you an idea on the history of the development of differential geometry, we would have to rely on what we relied not only in terms of mathematics but also in terms of philosophy. We will go back to the days of the early Greek when we found a person in the name of Eratosthenes is the first person who measured the circumference of Earth around 200 BC. We can call this will be the culmination and the starting point of measuring the circumference or any kind of a measurement related to Earth, and it planted the seed of differential geometry in terms of measurement. What we see next is obviously one of the great Greek pioneers, Euclid, in his book Elements, first carried the notion of measurement. Now, we have all read Euclid's during our school days, and the young people who are still reading Euclid's Elements is considered whatever we call as triangle, angle, length, measurements. Everything is there in Euclid's Elements, written in Greek language. It is the first and the foremost aspect in terms of defining measurement and creating a proper formal approach towards geometry. We call Euclidean geometry because we deal with notions and ideas which are written in Euclid's Elements. The first major attempt in order to find out differential geometry was made by this Flemish cartographer Gerardus Mercator. Now, Gerardus Mercator actually discovered something which is called a Mercator projection, and I am not going to give you more into Mercator projection, but the basic and the most significant contribution of Mercator was to develop a geographical chart or a map which is made out of our spherical globe of Earth. Now, it is Mercator who first perceived this notion that a spherical globe, or the measurement of the globe or earth, can be flattened out into a two-dimensional map. It is also noteworthy that in 1569 Mercator published the first world map and coined the term atlas. So Mercator, being a cartographer, made his first step and made a major contribution in differential geometry, although I would like to mention that Mercator knew about the pitfalls and the problems of this map design, which is flattening out a sphere into a flat surface, and was aware about the conformal nature of this projection. As we will go details into differential geometry, we will see that a sphere contains a positive curvature. It is impossible that you can flatten out a sphere into a flat Euclidean plane, which is a two-dimensional map and which has got absolutely zero curvature. Although Mercator knew about his limitation, yet his contribution is very significant. He developed what is called a geographical chart, and it helped during that time people out in the sea to make their navigation easily. In the middle stage, we come across this famous person, René Descartes, who introduced analytical geometry and which laid to the foundation of differential geometry in the further study. René Descartes, being a philosopher and a mathematician, also introduced Cartesian coordinates, and based on his analytical geometry, these three great personalities carried on further studies. Newton, Leibniz and Pierre de Fermat, they began the study of plane curves and inflections and circles of osculation. All these were based basically on Descartes' analytical geometry. So you see Newton, Leibniz and in further Fermat made important contributions in differential geometry in the study of the nature of the curves. Well, it is quite unusual in the history of mathematics that a single family has produced half a dozen outstanding mathematicians over a couple of generations. Yes, we are talking about the Bernoulli brothers, who has been quite important in contribution of differential geometry. The most outstanding three Bernoulli mathematicians, they were Jacob, Johann and Daniel. They were the three most influential experts in the academic community, yet they were very hostile to each other in terms of competition. They belonged to a prosperous family of traders and scholars coming from the city of Basel in Switzerland. Although Jacob and Johann developed a kind of a rather jealous nature of each of their brothers, yet they maintained a very competitive relationship. The family actually from Holland with a strong Calvinism religion came from Switzerland, and this is the Bernoulli brothers made significant contribution to the use of infinite symbols to study geometry. As we have seen that we have told that differential geometry is basically using calculus. So the Bernoulli brothers used calculus to calculate infinite symbols to the study of geometry. This particular book, which is called Analysis of the Infinitely Small to Understand Curvatures, is actually collated by another French mathematician called Guillaume L'Hôpital and later authored by Johann Bernoulli. It contains the tangents to plane curves of various types and which are computed using the condition dy equals to 0. Similar points of inflections are calculated. I would like to mention that Guillaume L'Hôpital is a French mathematician who first studied on the problem, what is the value of 0 upon 0? Is it infinity? Is it minus infinity? What it is? So it is basically called L'Hôpital's contribution, but later named into Johann Bernoulli's contribution. He and L'Hôpital and Johann Bernoulli, they studied a lot into the intrinsic curvature nature, and they studied, and it was finally put up into this book, which L'Hôpital actually collated. So Bernoulli brothers, another very important figure in differential geometry. Okay, so we have got someone, Alexis Claude Clara, around our 1713 to 1765, a French mathematician who studied space curves and tangent and subtangent. He is the first one who introduced implicit understanding of tangent spaces. Now, you might ask a question that what is intrinsic implicit understanding of geometry. We will let you know once we read Theorema Egregium by Carl Friedrich Gauss. But Alexis, he is basically a mathematician, astronomer, and a geophysicist, introduced the concept of tangent and subtangent direction to space curves in relation to the direction which lie along a surface on which the space curve lies. He demonstrated the implicit understanding of the tangent space, and he is the first person to coin curvature, double curvature, and principal curvatures, which were further extended by the prince of mathematics, Carl Friedrich Gauss. Well, what can you tell about this great person? Leonhard Euler, being a student of Johann Bernoulli, first used the analytical geodesic equation. This is very important later in differential geometry as well as in the developments of Einstein's general theory of relativity. Euler was the first person to introduce analytical geodesic equation, and which he also introduced the concept of intrinsic geometry, and most importantly Euler-Lagrange equations is very, very important in terms of modern differential geometry. Well, Gaspar Monge around 1700 made important contributions in the theory of plane curves. Most importantly, this great French mathematician is basically the inventor of descriptive geometry. Okay, and he made important contribution in terms of reforming French education. He is one of the founder of the great institute, famous institute, École Polytechnique in France. Well, Gaspar Monge made contribution in theory of plane curves and surfaces, and studies surfaces of revolution and envelopes of plane curves and space curves. So we see Gaspar Monge making very important contribution in terms of differential geometry. We have seen Euler, and we have seen earlier in terms of Pierre de Fermat and Alexis Claude Cloma, who are making important contributions, and we have already seen that the seed is planted. Usage of calculus in geometry.
So you saw a basic idea on the sequence of differential geometry, how it started with Eratosthenes and it went forward. But still we are stuck at one point. Who discovered the non-Euclidean geometry, or which point of our history triggered off the differential geometry? Here is a quick look.
To digging the roots where from actually differential geometry started, or who are the people and what are their works in order to which triggers of differential geometry, we will be lost. Because each of the contributions, each of the mathematicians' contribution is very important in terms of differential geometry. We started with Eratosthenes, and then we moved into Descartes, and then Pierre de Fermat, Newton, Leibniz. Everybody's contribution is important. However, historians and mathematicians, when they talk about the advent of non-Euclidean geometry, the immediate person that comes to our mind is this: Nikolai Ivanovich Lobachevsky, being a Russian mathematician born from 1792 to 1856. He is rightly considered by Kingston Clifford, the founder of Clifford algebra, as the Copernicus of geometry, because when we think of Copernicus, his entire foundations and his discoveries actually revolutionized astrophysics and astronomy. So Lobachevsky's contribution to geometry actually earned him the title the Copernicus of geometry. He is born in a moderate family, and his father died around about 7 years of age when he, along with his mother, moved to Kazan district in Russia. He is actually mentored by Johann Christian Martin Bertels, who was a former, I would say, a student as well as a close associate of the famous Carl Friedrich Gauss. So he was being mentored by him. He is actually the founder of hyperbolic geometry, and he worked at Kazan University. He received a Master's of Science and Mathematics, and he actually, I would say, worked on Euclid's fifth postulate. Now, for years, mathematicians have been trying to deduce Euclid's postulate from other axioms, but Lobachevsky created a geometry in which the fifth postulate is not true. Right. So his geometry was based on the assumption that in the plane formed by a line and a point not on the line, it is possible to draw infinitely many lines to the point that are parallel to the origin. It was later proved that his geometry was self-consistent, and this actually triggered off differential geometry. As you will see that when we speak of lines, right, which actually can be drawn infinitely through that point and they are parallel to the origin, that is basically what replaces Playfair's axiom of Euclid's fifth postulate, and he created a new geometry. However, some mathematicians and historians wrongly claim that Lobachevsky in his studies of non-Euclidean geometry was influenced by Gauss or something like that. But the fact is that Gauss himself appreciated Lobachevsky's work. So it is a matter of debate. So we won't go into that kind of a discussion. But the debate remains open. But Gauss actually appreciated Lobachevsky's contribution to hyperbolic geometry. So Lobachevsky, along with an Hungarian mathematician Janus Bolyai and the famous Carl Friedrich Gauss, actually they founded what is called hyperbolic geometry. So these three eminent figures contributed towards hyperbolic geometry, and as we will see that this actually triggered off the very starting point of differential geometry.
This picture or this book which you are looking at right now is written by the Prince of Mathematics Carl Friedrich Gauss. Now, you can just go through what I have written in the points. Now, one thing you need to understand that distance is basically the founding or cornerstone. It is the brick of Euclidean geometry. Now, what Carl Friedrich Gauss thought is that, for example, let me show you, although this is not the right. So, if you have got a curvature, something like this, and there is an ant living inside this structure, okay, so can that ant or that creature calculate the curvature of this particular object without looking outside? So that is the first notion, which is called intrinsic geometry. Now understand one thing, any object, for example this object or my watch or anything, these are thought that these are immersed in Euclidean spaces. Immersed in Euclidean spaces means this is in a triangle, in a box, in a parallelogram, in a square. The first genius stroke of Carl Gauss was that, can we take any object which is outside the Euclidean space? That means I am going to measure the curvature, the length of line, not in terms of any immersion into a particular space, a box, a triangle, or a polygon or parallelogram. I am going to measure the distance of two lines or two curves completely unaware of the external world. That means completely intrinsically. Now, he invented what is called Gaussian coordinates, the distance between two infinitesimally close points, which can be defined by the length infinitesimal short segment which joins them and which lies on the tangent plane. Now look, so first of all, what was the motivation? The motivation was that, can we define something without looking at the outside world? So a creature living at the outside can look into the surface and think, okay, this is bend, this is this. But what about the creature living inside? He has got no idea of the outside world, and he wants to measure the distance, or let us say he wants to make the geometry understand internally. Now look at the first picture. This is a classical Euclidean way of calculating distance between two lines. Now look at the second picture. Now if we want to calculate the distance between two lines, which I have mentioned it in red, immediately what we do is that we recall our school days, the good old Pythagoras' theorem. Now this is the general notion. This is way in which we distance, given any point between these two coordinates, which is called Gaussian coordinates, which has got some crazy curvatures which is there on the screen, we use Pythagoras. Look at this point, the picture number 3. We cannot apply Pythagoras' theorem here. Why? Because the axes are not perpendicular to each other. I repeat, the central idea is basically to define any length of any curve departing from one point and arriving at another point with the terms of data which is completely intrinsic. Look at this picture. Now what Gauss did is that this one which you see ds square equals to f all those things. I have given a basic idea. This is something which is called the Gaussian metric. I am just telling you, it was designed and developed in 1828, and you can call this as the first example of Riemannian metric, although Riemann was just 2 years old during this time. So what is the central idea? Let us forget those mathematical part which we can deal in a separate video. The basic idea is that how we can, we started with Lobachevsky, who designed hyperbolic geometry, and then that was triggered the differential geometry part. And Carl Gauss, the basic motivation is that how we can understand the geometry, length of curvature, everything without looking outside, totally intrinsically. The problem arises because the axes are curved, we cannot apply Pythagoras' theorem. So this is the equation which he designed. This is the Riemannian metric, which is, I would say, the Riemannian metric, which is later called. Definitely it would be expanded into a tensorial form in a much later phase of the development of science. This was basically how we term that the foundations of differential geometry becoming externally free and defining it in terms of internal geometry. This is the first seminal contribution of Gauss, designing what is called the metric, the first definition of the second big person to come in the world of differential geometry is this person. I don't need to explain him further. I call him the granddaddy. With the appearance of Bernhard Riemann in the world, the differential geometry was totally set ablaze. Now, before I go and explain, just a quick point on the significant contributions of Bernhard Riemann. The first paper, which is right there in your screen, this one is basically the thesis paper of Bernhard Riemann. Bernhard Riemann is a true genius. He suffered from poverty, he suffered from health problems, but somehow he is a true genius. Here is some of the quick points. On June 10, 1854, Riemann read his thesis. Dedekind, his one kind of a biographer, said that it is a milestone in the history of geometry. The lecture that he gave was published in 3 sections. First, the topological notions. Second, the metric relation. And third one, application to physical space. First section introduces the idea of continuous manifold as a collection of objects. Second section includes metric and relation, and developed here what he provides the foundation of Riemannian differential geometry. He also introduces something which is called geodesic normal coordinates, a very important part of differential geometry, manifolds of constant curvature, figures which can be moved arbitrarily in between them, and he invented elliptic geometry. To define the contribution of differential geometry, it is totally out of the scope again of this video. It is immense, it is huge. I was reading one of the research papers which lays out more on the foundations of Riemann geometry. I read a wonderful line. It is called that Riemann's contribution in differential geometry is not evolutionary, it is revolutionary. Figure a kind of a mathematical equation which is there in the screen. It introduced n extended manifold whose points are labeled by n rather than 2 curvilinear coordinates, and introduced the line element as a generic symmetric quadratic form in those differential of these coordinates. So as you can see, I have just pointed out here that the coefficient of this quadratic form, which is later known as Riemannian metric tensor, I would just like to tell you that later with the students of Bernhard Riemann, it was further extended into tensorial form. Now this is something important. I will just try to make a note. Riemann grasped the main point, namely that the geometry of manifold, obviously we are talking of the geometry of manifold, right, the geometry of manifold is encoded in the possible metric tensor and measured relations, right? So what happened is that with Riemann joining the show with Carl Friedrich Gauss, we have got first, we freed ourselves from coordinates. We got something which is called hyperbolic geometry. We got now something which we want to measure arbitrary manifolds. We want to measure intrinsically, not extrinsically. We got Carl Gauss who freed the Pythagoras' theorem and divide a kind of a metric. So a manifold which has got a metric, it measures the length. Now, here is a small note. The generic connection of the tangent bundle, I don't want to explain what is a tangent bundle. It is called an affine connection. And there is something which is called a Levi-Civita connection. I know I'm going a little bit technical. The Levi-Civita connection is a kind of an affine connection. So the metric actually connects with a connection which is called a Levi-Civita connection, and this measures something. We will come to this part, and this connection, affine connection, relates with the Riemannian geometry, Riemannian curvature tensor. So I will just like to read these things out because there are so many things it's very difficult to remember. The primary concern of the new differential geometry, as founded by Riemann working on the works of Carl Gauss, was that defining length of curves on arbitrary manifolds. This is obviously quite true, that our main task is to define length of curves on arbitrary manifolds. Now, when we define curves on arbitrary manifolds, what happens is that we try to preserve the angle so that calculations become easy, and we try to go on parallelly transporting things from one point to another. So parallel transport is something when we call that what we call is that the vector is parallelly transported along the arc between. So the angle between the transported vector and the arc. Let me read it out. We say that the vector is parallel transported along an arc of curve if the angle between the transported vector and the tangent vector is preserved. Now, I would like to make a note that if you see my video on what is called Ricci scalar parallel transport Ricci curvature tensor, which is there in my differential geometry playlist in my channel, you will get a complete understanding of parallel transport. We are doing parallel transport just to get a easier way of calculating the length of curve. Now, when we parallel transport something, then we try to calculate the angles which are conserved, and that parallel transport notion is first done by another great mathematician, Elwin, Bruno, Christoffel. Christoffel symbols are something when we do a kind of a parallel transport, it tells at a given point that how much it vectors infinitesimally change. So when we are doing a parallel transport, that transported vector along with the parallel vector, how much it is being change, or I would say that infinitesimal change, how much it is being done, and that calculation is actually done through Christoffel symbols. Now, let me explain you in one way. Whenever we are calculating on a manifold the change in structure, it is generally assumed that when a vector changes, what happens is that the basis of the vector always will remain the same. If you have noted my videos on tensors, there's a list of videos on tensor, I have spoken that the basis of the vector is always changing. But in case of this kind of a geometry, more complex geometry like Riemannian manifold, etc., the basis of the vector also changes. Herein lies the problem. So even if the basis of the vector changes, we cannot use partial derivatives. We use something which is called covariant derivative. So the part of the covariant derivative that keeps track of the changes arising from the change of basis. So the change of basis is actually the culprit which is causing the change. So the part of the calculation which causes the change in the basis is actually taken care by Christoffel symbols. Christoffel symbols keeps track of the changes arising from the change of basis. They encode how much the basis vector changes as we move along the sphere or this kind of an arbitrary manifold. I hope I can make things clear. I am not sure. You need to look into the mathematics part, otherwise it will be difficult. Now, before we go ahead into the next part, you need to also understand that at some point of time in general theory of relativity, Christoffel symbols, although it will be wrong to tell, measures gravity. Now you might ask the question, why? Now let me give you a very simple explanation. The gravitational potential which changes along the manifold, which causes the curvature of space-time, that change happens because the basis of the vector changes as the object starts moving in the smooth manifold. And because the basis of the vector changes, and because the change in the in the space-time causes curvature. So in one way we can tell that Christoffel symbols do take into account the changes or the gravitational change. The address reads Corso Giuseppe Garibaldi 41480222 Lugo, RA, Italy. Here is where the famous Italian mathematician Gregorio Ricci Curbastro was born. The plaque that you see is right in front of his house, and it means he gave science the absolute differential calculus, an indispensable tool for the theory of general relativity, a new vision of the universe. Now, I always feel that it would have been a chance, given a chance, I would have stood in front of the house of Gregorio Ricci Curbastro and taken a selfie or made a video. Anyway, so the basic idea is the appearance of Ricci Curbastro. In many ways, he contributed to differential geometry. Let us look into this picture. I will give you a basic idea. He was born in an aristocratic family, studied in the University of Rome and then in Pisa. He met with Luigi Bianchi. Bianchi was influenced by the teachings of Ulisse Dini and Enrico Betti, Enrico Betti is considered the father of modern topology. Though through Betti and both Ricci and Bianchi, they introduced a new concept which is called a Ricci tensor. So now you see with the appearance of Riemann and then forward by Christoffel and now by Gregorio Ricci Curbastro, differential geometry got a new way of understanding. Now, Bianchi Luigi Bianchi will come. What is the contribution of Bianchi? Ricci Curbastro invented what is called a Ricci tensor. Here is a small picture. Now, it would be difficult again in this scope to explain what is Ricci tensor does. If you want, go back and look into my video. You will get a thorough understanding of Ricci tensor. Just to tell you that Ricci tensor, as you can see, that it is being expressed in terms of Christoffel symbols, tells how a shape is deformed as one moves along a geodesics in the space. Given a sphere, we measure the curvature more as the object diverges. The more the object diverges, the more is the curvature. The less is the divergence, less is the curvature. So in a given sphere, which has always got a positive curvature, it will always, when you are moving a ball, it's difficult, right, to explain. When you are moving a ball, say for example, a ball is moved along a sphere. So if you start here, and it moves up, you will see that the shape of the ball is deforming. And you start, and so in a sphere. But in this kind of a shape, you will see that the shape of the ball is converging. So one is flat Euclidean space where there is no change in volume. One is a positive where it converges and the shape deforms, right? And another is negative where it shrinks down. I have explained this. So now you see that I forgot the name. Just let me look back. Who was the person? So I remember what is called Carter, the first person who developed Mercator. Right, Mercator projection. So you see that during that time, Mercator, realized that a sphere cannot be measured in a flat space. Because he developed an atlas. Right, so he knew that there are problems in terms of his calculation, that a sphere cannot be measured in flat space, and the spaces between the continents and the ocean will carry definitely some problems. Here also now you see that in a sphere, when we make that sphere into a flat surface, it will definitely make changes into the spaces between the continents, ocean and country. Same appears here. Are you getting my point? If a flat surface, a sphere is made into a flat surface and it contains error, similarly in a sphere, if you're trying to move an object, particularly a ball, up the way, then definitely it will be deformed. And Ricci tensor actually tells you how a shape is deformed as it moves along geodesics in a space. we call the shortest movement in that particular curvature is something which is called a geodesic. One point I would like to tell you for the students, don't make a mistake that manifold is something which can be called in a Euclidean space. No, manifold is always on something which has got a curvature. Positive, negative, that is a different issue. But manifolds cannot be told that a flat Euclidean space, it has a manifold. Manifolds always demand that it should have a curvature. Here is this handsome gentleman, Bianchi. Okay, so Bianchi's contribution, if you talk, it is basically to rediscover what is called a Bianchi identity. Now, when I talk of rediscover, you might ask me a question that, does that mean that it was already discovered? Yes. History says, I have just taken a note, in 1922, when Bianchi discovered Bianchi identity, it is said that it was already discovered by Gregorio Ricci. So it might be he had forgot or something. So Bianchi was deeply influenced by Ulisse Dini and Enrico Betti. So Bianchi's major contribution was what is called Bianchi identity. This is the picture. This shows that the Ricci tensor is symmetric, 1. The second picture is there on the screen. This is the second differential identity, which states that its divergence is equal to 1/2 of the gradient of its trace. And by definition, this is the third one, which is named as the curvature scalar. Now, the Bianchi identities were precisely the clue which led Einstein to develop, which is something called a covariant physics. Okay, so with the help of Marcel Grossman, who is one of his friends, you can look into my video, which is called The Architects of General Theory of Relativity. You will get an idea. But anyway, with the help of Marcel Grossman and with this Bianchi identity, Einstein formed what is called covariantly conserved tensor. Now, if you have read tensor, you know what is contravariant and what is covariant. You can find out those lectures in my playlist in tensor. So covariantly conserved tensor is something which Einstein found it, and it also plays a major role on the left hand side of Einstein field equation, which actually tells the propagation. Now, the left hand side is something where you can find the Bianchi identity or the covariantly conserved equation, and what is in the right hand side, we have got stress energy momentum tensor. So both of them are equal to each. Now, these are actually the foundations of differential geometry. I mean to say, the way differential geometry actually moved, starting from the Euclid's time, starting from Eratosthenes, and then we moved into Carl Gauss, Bernhard Riemann, and further. Now, but you have to note one thing, that we are still stuck with the classical era, right? I mean to say, the basic notion of differential geometry, till now what we saw is still we are stuck into the classical era. But what about the modern era? What about the developments in this century, what is happening right now? Here I present a very small, I know there are a lot of mathematicians and important people I have missed, but as you know, we have to make videos in a certain stipulated time. Here is one small snippet or small presentation on who are and what are the recent developments and changes which are happening in modern differential geometry.
Well, the modern differential geometry emerged early in 1900 along with the foundation contribution of many mathematicians, and among them first we encounter Henri Poincaré on the foundations of topology around about 1900. So we see the contribution of Henri Poincaré's contribution in terms of topology first laid the foundation stone for differential geometry. Well, the notion of topological space, which we often call the Hausdorff space, is being first founded by Felix Hausdorff, is considered one of the founders of modern topology. Hausdorff's father, Louis Hausdorff, was a Jewish merchant. And just to add more to this, I would like to tell you that Felix actually suffered a lot being of Jewish origin. From 1887 to 1891, he studied mathematics and astronomy in the Leipzig University, and in December 1901, Hausdorff was appointed as adjunct professor at the University of Leipzig. As a Jew, his position became very difficult. In 1941, he was scheduled to go to an internment camp, but somehow through some of his influential friends and colleagues, he managed to avoid. On the night of 25th of January 1942, both Hausdorff and his wife committed suicide, and they were dead by the 26th of Jan. However, the significance and contribution of Felix Hausdorff continues as the founder of topology and topological space. Elie Joseph Caton, an influential French mathematician who did fundamental work in the theory of Lie group and differential geometry. So you see, Elie Caton helped reformulate the foundations of the differential geometry of smooth manifolds in terms of exterior calculus. Well, if you want to know what is exterior calculus, it is a bit technical term. However, exterior calculus is a branch of differential geometry that generalizes the concept of differentiations to antisymmetric exterior derivative. It is generally called as a generalization of the fundamental theorem of calculus to Stokes' theorem. This gentleman, Jean-Louis Cozoul, actually first introduced the concept of vector bundles. Vector bundles are topological constructs that makes precise the idea of family of vector spaces parametrized by another space. So first we started with Poincaré, then we moved to Felix Hausdorff, Elie Caton and Jean-Louis Cozoul, introducing the concept of vector bundles, laying the foundation of modern differential geometry. Xing-Shen Chern. Well, this person is considered to be the father of modern differential geometry and is widely regarded as a leader in terms of geometrical studies. Well, Xing-Shen Chern graduated from Nankai University in Tianjin in China around 1930. He got his MS degree in 1934 and he received his doctorate from Hamburg University, Germany in 1936. His fundamental contributions to differential geometry has been many. As you see that I have listed down few of his contributions which are highly technical to discuss: Chern-Class, Chern-Gauss-Bonnet theorem, Chern-Weil homomorphism and Chern-Simons invariance. The physics Nobel Prize winner C.N. Young once said that Chern is as par as with Euclid, Gauss, Riemann and Cartan. He worked for a long time in Institute for Advanced Studies at Princeton, and where he met Philip Griffith, the then president of IAS, who wrote, "More than any other mathematician, Xing-Shen Chern defined the subject of global differential geometry, a central area in contemporary mathematics. His work spanned almost 7 decades and he helped to shape large areas of modern mathematics." Well, to be very honest with you, I have read about Xing-Shen Chern and it is too technical, but you can consider that he has got a huge amount of contribution in terms of differential geometry, developing a Chern class, and his works actually goes from general theory of relativity to invariant theory to cohomology theory, fiber bundles, Sheff theory and whatnot. So definitely Xing-Shen Chern's contribution to modern differential geometry cannot be ignored, and he is rightly considered to be the father of modern differential geometry. His student Xing-Tung Yao, he is a student of Xing-Shen Chern and he was awarded Fields Medal for proving the Calabi-Yau conjecture. Now, if I talk of Xing-Tung Yao, yes, I read a news that he has been entangled with a controversy with Gregory Perlman. However, let us leave aside those controversies and let the world decide. 1949 he was born in China. He went for PhD at University of California in around 1969. There he read Journal of Differential Geometry and was deeply influenced by John Milner's paper on geometric group theory. Yeah, so John Milner's papers on geometric group theory actually created the first flame within Xingtung Yao to create and make his career in geometry. He received his PhD in 1971 under Xing Chern, and his most widely celebrated results are one, which is called boundary value problem for Monge-Ampere equation. Second would be the positive mass theorem, and we would be happy to tell that positive mass theorem is actually refers to a collection of fundamental result of general theory of relativity and differential geometry. It actually states that gravitational energy of an isolated system is non-negative. He also worked with Donaldson and Karen Uhlenbeck. I think you know about Karen Uhlenbeck, American mathematician. She won the Fields Medal also. So it is called the Donaldson-Uhlenbeck-Yau theorem. His contribution also to Calabi-Yau conjecture, topological theory of minimal surface, and he is also the founder director of several mathematical institutes. As you understand, he is rightly called as the right son of Xing Chern, because as per the master, he is the right disciple and is immensely contributed in terms of differential geometry. 1930 we come close to Sir William Valence Douglas Hodge, who is quite known for his Hodge theory. Now if you ask me what is Hodge theory, this is not the right platform right now to decide. However, this is a very important contribution in terms of differential geometry, which we can definitely read it later. Next we come with another gentleman called Ernst Mann, and in 1950 he first introduced the theory of fiber bundles. Now again this would be a little bit technical in order to mention what is fiber bundle, but let us understand for this that Ernst Mann connections and fiber bundles are a very important connection in terms of differential geometry. Lastly, we'll come to a great personality, Sir Michael Francis Atiyah. Now, to be very honest with you, to tell more about Michael Atiyah, it would require more time. However, I would tell you that he won both the Fields Medal and Abel Prize. Particularly, Michael Atiyah is known for K-theory, Atiyah-Singer index theorem, which deals with further with instantons and monopoles, and Atiyah algebroid and Atiyah conjecture. Michael Atiyah, if you have read my, what I would say, interview with my Professor Daksh Lohia, he encountered Sir Michael Atiyah in one of his discussion at Cambridge University, and he is a true genius. It would require a complete video of almost an hour to discuss about Francis Michael Atiyah, because his contributions are immense. And just to tell you, he also collaborated with three mathematicians. This person on your screen is called Raoul Bott, who is very famous for this Atiyah-Bott fixed point theorem. The next person would be Isidore M. Singer, who collaborated with Professor Atiyah to develop the Atiyah-Singer index theorem, which Michael Atiyah is mostly famous. And the last person is Friedrich Hiselberg, and he collaborated with Friedrich Hiselberg to develop what is called the topological K theory. So that is all. That is in short just to tell you who are the contributors, and we ended with a great person, Michael Francis Atiyah, whose contributions on the field of differential geometry is beyond, I would say, beyond comprehension. So we started with Poincaré and we ended with Michael Atiyah, and among them we saw the Hodge theory, we got fiber bundles, vector bundles, all definitely contributed to the development of differential geometry in terms of modern context.
So that's it. My attempt to make a kind of an introduction to differential geometry. Do you want me? Let me just summarize what we learned. So first, I have to look back to my notes. Don't take me wrong. First, we understood what is a differential geometry. Then we understood why it is called differential geometry. We understood why it is called differential geometry. Then what we got, what is called, why do we apply calculus in differential geometry? We also understood what is called a smooth manifold. Most importantly, we also understood that why we need to go to abstract space from the general definition of something definite. We also answered the question, which one should I study first? Is it differential geometry or topology? I've given an answer. We also learned why should I learn differential geometry, basic notions, the industry practical experience. We got to learn that is differential geometry difficult? Absolutely not. I'm coming up with a plan that things will be much easier. We learned a lot about history of differential geometry. The basic take home part of differential geometry's history is that we started with something solid, Euclidean, and then we moved out into something into abstract, and then we moved into further abstract, smooth manifolds, and then we also learned that how we can define geometry intrinsically with Carl Gauss. With the advent of Bernhard Riemann, we extended to n dimension. Then we learned he is the inventor of elliptic geometry, the first what is called the geodesic normal coordinates. We also learned that with the help of Christoffel symbols, how we can measure the change of the change in the movements of vectors in case that the basis of the vector also changes. We also got a notion that Christoffel symbols gives a kind of a idea on the generation of gravity. We also got an idea of what is the contribution of Ricci Curbastro. Obviously, this is with the help of Ricci flow, which was invented by Richard Hamilton. Our millennium problem was solved by Grigori Perelman. So we learned what is a Ricci tensor. Then we learned what is called in Bianchi identity and how this Bianchi identity helped Einstein to formulate what is called a covariantly conserved tensor and form an equation. And we also learned what are the new developments and activities and researches which are going on in modern differential geometry. I think that is quite an exhaustive kind of a video. I will wait for your comments. I have a bad habit of making videos little bit long, but I believe in something that you cannot make this kind of a concept understood until you have got a strong, proper foundation which starts from something and gives you a total understanding. Thank you for watching this video. Do let me know your comments and whatever you feel like, and please don't forget to like and subscribe. Thank you very much. Keep on studying differential geometry. I'm coming up with a complete plan on how to learn differential geometry with suggestions, books, and a definite method of studying. Thank you very much. Stay safe and stay happy, and have a nice day ahead. Bye.